Hello again and welcome back, hopefully, to the Hive series on PCB design with KiCAD. My name is Ben, and in this series we've been walking through the PCB design process using KiCAD as our electronics design software. If you haven't seen video 7A yet, I recommend that you go and see that first, although you don't need that to go through this video. The previous videos went through the design process all the way through, resulting in a completed PCB ready for fabrication. One thing I mentioned during that process and was featured in the original EDA design flow in part 2 was library management and the idea of using project scope libraries only. But when we actually did the design, I actually ignored this for simplicity and time constraints. In the last video, part 7A, we made a new project-specific footprint library and populated it with a bunch of globally available footprints that we needed. In this video, we'll look to generate a custom footprint from scratch for the battery holder, why you should never do it again, and then how to import an online model. This material is, of course, not required, for functional design, but it is good design practice for KiCAD at least to keep all of your parts in a project-level library. Because this is not directly related to the design flow of the previous videos, I'll make no assumptions about the state of your system or knowledge other than that you've watched part 7A. So I apologize if some of this is repetition for some of you. Let us get started. So we ended the last video with 6 of the 8 footprints in our new library and only the battery holder and the IC left. We're going to start with the battery holder here. You should always first try filtering for the part like we did with the other footprints because you never know. But if you do that, you will find that we don't have this. It doesn't exist. So we're going to be making it. Now let's go find the data sheet. Now, generally, you wouldn't actually making it wouldn't be your first option. You'd go and hunt it down. But the point of this video is to actually make it. So we're going to do that first. Hunting down the technical drawing for the datasheet or for the battery holder, I had to go to the manufacturer's website because the datasheet link on DigiKey gave me their catalog, which is totally not helpful. So anyway, this is what the technical drawing actually looks like, or at least the top half of it. And on the right-hand side, it gives us this lovely suggested PCB layout, which is great. We're going to go draw this without all of the dimensions, obviously. There are 2 options for making footprints in KiCAD. You can either completely start from scratch, like a blank sheet of paper, which is good for distinctly non-standard parts, like this battery holder, for instance. Or you can use the wizard, which is much better, assuming that your footprint is standard or nearly standard. Otherwise, that's going to be really hard to do. So unfortunately, ours is non-standard, so we're going to create a new empty footprint. That's the left icon there. Give your footprint a name. I use the standard manufacturer _ part number for MPD _ BC 2032-42. And I set it to a through-hole component rather than SMD because it is indeed a through-hole component. It has pins that go through the board. This will give you a blank footprint that looks like this with a reference designator that's empty right now, and the part number or part name that's in gray. Always make sure to set your units first. Units should match your data sheet or drawing on the left there. Our drawing is in millimeters and in inches, so we're actually going to leave it in millimeters. It has both units on it. There is no set order to this, but I personally like placing all my pads first. So we're going to go to the Add Pad icon here on the right or under the Place menu. Left click to drop the first pad wherever, and then drop a second pad as well. Hit Escape to exit. We're actually only going to place one to start and then set its properties and copy it. Great. If you made a second pad, you can easily just click the second pad and hit delete at this point, or you can rerun through the properties settings later. Either way is fine. Let's select the pad and hit E, or right click and go to properties to open the pad properties window. Looks like this. Pad generation is quite flexible. There are 5 options for type, but ours is definitely going to be a through hole and leave it as pad number 1. As we saw during the design, if you were saw those videos, you want to match the pad numbers and the symbols pin numbers. The battery symbol uses 1 for the positive terminal and 2 for the negative terminal, so we want to match those numbers with our footprint. Let's take a look back at the drawing. These are actually slots, not holes, so they're not circular, and they're not actually the same size. So the left one is, that is 0.8 millimeters in X and 4.1 millimeters in Y, and the right one is not 0.08, but 0.8 millimeters in X again, and 2.3 millimeters in Y. And you know that the bigger one is in millimeters and the smaller one is in inches, just because of the size difference. So we can adjust the hole shape and hole size to to an oval and 0.8 and 4.1. The preview definitely looks a little bit funny now because that annular ring is still a circle, and it's a circle around a ovular hole, so that's a little bit odd. So we're going to go ahead and change the pad shape. Let's change it to rectangular. So pad 1 of any footprint is always going to have some sort of marker. For an IC, that's typically going to be like a silkscreen dot or like a star or like a little triangle thing. But for through holes, that usually means a different shaped pad, often rectangular, or square, or octagonal. So how big should the pad be? Sadly, the drawing isn't very useful here. That's pretty unfortunate. But remembering that the pad diameter for a circular pad is twice the diameter of the hole, we can make the X diameter of this pad twice the width of the hole of this slot, and then use the same thickness to add to the Y dimension. So since the hole is 0.8 by 4.1, that means the pad's X dimension is going to be set to 1.6 millimeters, which means the Y dimension will also be 0.8 millimeters larger than the hole, or 4.9 millimeters. So let's set that here. The angle rotates the pad and hole. We're going to leave that at 0. Voila! Much better. That looks a lot cleaner. The copper layers box says which copper layers the pads are going to interact with. There are a couple of different options. You can either interact with all the layers, like in the image on the right. It could interact with just the top, the bottom, and any internal layers that it's connected to the same net. So just, say, whatever. Alternatively, it can attach to only the connected layers, i.e. either the top or bottom plus any internal connected layers. Or if it's non-electrical, just hit none. We're going to leave it as all copper layers. Easier that way, and frankly ours is only a 2-layer design, so it really doesn't matter. And as I mentioned, a model of the hole connections is on the top there. The technical layers determine if the holes will interact with any of the other layers. Usually the mask layers are fine. This defaults is totally okay. But lastly, we need to set the position. We could do this by setting the grid and moving it manually, but usually the pads are particularly placed, so giving it an exact position is better. Back to the drawing. Always a good idea to center the part at the origin, which also makes the dimensions a little bit easier. Because the pads, as seen here, are right along y equals 0 and are spaced 27.2 millimeters apart, we know that the left pad is going to be placed at 13.6 millimeters to the left, which means that it'll actually be negative 13.6 millimeters. Back to our pad properties, we can easily set that as the position X will be position X will be minus 13.6 and position Y will be 0. And with everything set, we can now click OK. Looks good. So if we didn't make the second pad, we could just duplicate or copy and paste this pad and then open the pad's properties window again. Alternatively, you can just right-click. If you made your second pad already, you can always right-click and just enter the pad properties window that way. So if you've copied it, some of these components will be, or some of these settings will be the same and be correct already. If you didn't copy it, then you'll need to update a couple of them. But assuming that you've copied it, like I did, we're going to set this pad number to 2. Don't forget to do that. We'll set the X position to 13.6 millimeters instead of negative 13.6 millimeters. And the pad shape also needs to change since it's no longer pad 1, so we're going to set it to oval. The size will transfer nicely. You could also have set it to rounded rectangle, but there's no need for fanciness here. Note that I actually botched this this design here, this layout. See how easy it is to do? The negative terminal slot actually is 2.3 millimeters and Y, not 4.1. So don't be me. Go change that here before you continue the part. Now, if I left it as 4.1 and had it fabricated, it would still fit. The hole would still be big enough, so it wouldn't be a disaster, but it wouldn't be great. That's a lot of solder to have to like fill that hole with. Anyway, whenever you're done, you can go ahead and click OK. Nice. Or it would be if the slot was correct, but that can actually be changed later, so it's not really that big of a deal right here. So the next step after making your pads is to actually draw the part outline. KiCAD recommends 3 slightly offset outlines. One on the fab layer for the fabrication house, one on the silkscreen layer for the assembler, and one on the courtyard layer to prevent part overlap. All right, let's take a look at the part outline. So how accurately you draw this outline is sort of up to you. Do you need to get an exact rendering, or is just a box okay? Depends on your requirements. This footprint outline is actually going to be pretty obnoxious to draw in KiCAD due to the non-primitive shapes. We can draw arcs, but you're basically specifying the start and end coordinates and a radius, and there's not really a lot of info here, so there's going to be a lot of kind of math and like figuring out exactly where stuff goes. So I didn't spend a lot of time on the outlines. I opted for just a couple of circles, because frankly that would have been a pain, and I really just don't care that much. So the fab layer circle approximates this part outline with a circle diameter equal to the maximum X dimension given in the drawing of about 28.96 millimeters. You don't really want to overlap graphics because it's really hard to see them, which is why KiCAD recommends placing the silkscreen outline, which we printed in ink, immediately outside the fab outline, like just slightly outside of it. That way you can see that they're another circle. The circle is sized to be slightly larger than the fab circle by half the line width of the fab layer and half the line width of the silkscreen layer because the sizing is measured from the middle of the line. This line width can be found by looking in the properties of the circles drawn on those layers. Lastly, the courtyard outline should be sized to have a 0.25 millimeter clearance around the silkscreen outline, which is added to the radius. These sizes were written in this image in purple on the user.comments layer, so they won't actually show up anywhere that gets made. Boy, that would have been quite a pain to deal with on the real outline. Do you get that? Like all of the different arcs and lines, everything has to be shifted out a little bit. That would have been awful. Frankly, it wasn't even that nice with these circles. So we also want to move the reference designator, that ref star outside the outline so the assembler can actually see it after it's been populated. My grid was a little bit large, so while moving the ref text, I right-clicked to open the context menu and adjusted the grid through the grid submenu to be half as big as it was so I could actually put it where I wanted it to. Great. I also added a little plus and minus symbol on the F silkscreen layer using the line tool to indicate polarity of the part since the circle doesn't have an orientation. I didn't talk about it, but if you wanted to add filled zones or polygons for some reason, you can also do that in the footprint as well, just with the add filled zones option or Control-Shift-Z. And that is our entire part. You could leave the name in the middle. That's totally okay. Don't forget to double check them with the measure tool and then save your work. Measure tool's highlighted here. You can also access it Control-Shift-M. Whew. Yeah, that was a whole process, especially the outline bit. It's really awful. That's really unpleasant, especially with more like if you're already doing non-standard components, the expectation is the outline is going to be non-standard, just not really something you want to be doing a whole lot of. Frankly, and it's not always possible to simplify and just draw circles, and it's always also possible datasheets won't be any good, so making this custom footprint generation just really nightmarish. Thankfully, most of the time we don't have to do this because we can either locate or request these models from Ultra Librarian or SnapMagic, although it definitely happens that you need to make this. Like this is a thing that you might well come across at some point. Suppliers often, if they have parts, or if Ultra Librarian or SnapMagic have them, the supplier will sometimes link to those like this. Footprint and models page looks like this. They give you a 2D step file, or sorry, a 3D step file. That's a typo. At the top for this one, We can scroll down to see set of models from Ultra Librarian or from SnapMagic. Which to use. There's no right or wrong answer. Both are very likely to be sufficient. It is up to you to confirm that, though, as with all footprints. I'm going to use the SnapMagic one because I prefer the footprint. It looks better, and there's also a 3D model. So you can just download it using the Select Download Format button and select the KiCAD version 6 or later. Obviously, select the model or the format that is aligned with your software if you're using something else. I also really like to add the 3D CAD model because I like to add the 3D model into my parts. It downloads a zip. You can unzip these where some are accessible. There are 5 files: the symbol, the footprint, the 3D model, how to import, and a license text file. In the footprint editor, you right-click your library and click Import Footprint, and then you're going to navigate to that KiCAD model file and open it. Notice how much nicer it looks. Also notice the 3 outlines. They also intelligently put the positive indicator outside the part outline, meaning the user can actually see it after assembly. This would be a good opportunity if you remember our failure in the design to match pin numbers and pad numbers together with the battery holder. This would be your opportunity to edit this to make it 1 and 2 instead of P and N. Once you're done with all of that, you can then go ahead and save it. Just imagine how annoying it would have been to make all those calculations, though. Rename it if you'd like. The default manufacturer _ part number is very effective and very standard, and you can filter for your library to save it into there, and then hit save. Woo! My goodness, congratulations. Look at that. We've got a footprint for our battery holder, and that will end part 7B and our discussion of making footprints from absolute scratch. As you've seen, it's not the best process, and it's really, really error prone if you're not super, super careful. So it's highly advised to find the model online, or at least request that be made from someone else. As always, a PDF of this video is available below, linked in the description, and hosted on the Hive's Wiki. In the next video, part 7C, which is currently the last video in our series, we'll cover using the footprint wizard, which can be used to generate standard or pseudo-standard footprints more easily. Or it could be more difficult. Guess we're going to find out. I will see you there.